A slow-moving stream travels in smooth, predictable layers. But move that same volume of water over a rocky riverbed, and it breaks into a chaotic mix of swirling eddies. Predicting the exact path of a fluid as it transitions from order to disorder is the first hurdle in designing any hydraulic system. To solve for these paths, we use fluid kinematics. Hydrokinematics deals with the geometry of motion, mapping velocity and acceleration across space and time. We strictly set aside the physical forces. Instead of calculating pump pressure or gravity, we focus entirely on the mathematical shape of the flow itself. Categorizing these flows into 5 specific pairs allows an engineer to move from simple observation to the precise math needed to calculate the forces required for a functioning system. We can simplify the most common classifications by isolating them into concepts of time and space. We anchor steady flow to time. If the velocity at a specific point in a pipe never changes as the clock ticks, the flow is steady. If the speed or direction at that point fluctuates over the next hour, it's unsteady. We anchor uniform flow to space. Flow is uniform if the velocity remains constant as a fluid particle moves from point A to point B at a specific instant. In a straight pipe of a constant diameter, the flow is uniform. In a narrowing pipe, the fluid must speed up to get through the gap, meaning the velocity changes over that distance, making it non-uniform. This is where a common logic trap occurs. It is easy to assume that if a flow remains steady over time, it must also be uniform across the length of a pipe. However, these are 2 separate properties, and the math changes significantly depending on which one is varying. Our third category is dimensionality. As seen in these diagrams from Figure 6.2, we classify flow as 1D, 2D, or 3D based on how many spatial coordinates, x, y, or z, are required to map the changes in the fluid's velocity. Fourth is rotation. Looking at Figure 6.14, we can see the difference between translation and rotation. Flow is classified as rotational or irrotational based purely on whether the individual particles spin around their own center of mass as they travel. Finally, we categorize the smoothness of the motion. Laminar flow occurs when fluid slides in parallel layers. When those layers break into erratic mixing and overlapping eddies, the flow becomes turbulent. Assigning a flow to the correct category across these 5 pairs dictates which mathematical models an engineer is allowed to apply to their system. To prove these categories mathematically, we use partial derivatives. For steady flow, the change in velocity with respect to time must equal 0. For uniform flow, the change in velocity with respect to the space coordinate, the distance traveled, must equal 0. Let's apply these rules. Imagine water flowing through a narrowing pipe at a constant rate of 5 liters per second. How would you classify it? It's steady, non-uniform. Constant input means velocity over time is unchanged, but the narrowing pipe forces fluid acceleration across space. Relying on these derivative rules prevents design failures. If an engineer assumes flow in this narrowing pipe is uniform, they miscalculate the pressure gradients, leading to a system that might work on paper but physically burst under the actual forces. These geometric rules are used daily in high-stakes environments. Aerospace engineers use the assumption of irrotational and steady flow to predict the lift generated over an aircraft's wing. Civil engineers designing cross-country pipelines strive to maintain steady and uniform flow. By keeping velocity constant across time and space, they minimize energy-draining head loss over hundreds of miles. This summary from the textbook reinforces our core rules. Kinematics is the geometry of motion, where time determines if a flow is steady, and spatial distance determines if it is uniform. Defining this geometric baseline is what allows us to eventually calculate the massive physical forces in the next chapter. If you can define what a streamline is based on these concepts, let us know in the comments.